Hello friends, welcome to engineering tutorial. So here we'll discuss the elastic behavior of solids in terms of spring ball model. So previously we discussed the elastic behavior in terms of the interatomic forces and potential energy. So here we'll try to understand it with the help of a physical model which resembles how the interatomic forces act to restore the the original shape and size of an object. So basically we try to understand the elastic behavior of solids. So elasticity, when a body undergoes deformation, that is change in its shape and size, and after the removal of the deforming force it retains its original shape and size, it returns back to its original shape and size, that is called as elastic behavior and is called as a elastic body. So the deformation in this case is temporary. After the removal of the deforming force, the body regains its original shape and size. Now this is basically because of the interatomic forces. So we can visualize the object as a collection of atoms which are placed in well-defined positions in a proper geometric pattern, and it has a certain separation distance between them initially undisturbed, which is called as the minimum potential energy equilibrium separation. This is called as the equilibrium separation gap. When the external deforming force, it changes the position of the atoms, it disturbs the position of the atoms, whether they go away from each other or towards each other. The interatomic force, it always acts opposite to the external deforming force. It can either be attractive in nature or repulsive in nature. The objective of the interatomic force is to restore the atoms back to their original equilibrium position. Okay? The objective is to return the atoms back to their original equilibrium position. This we studied in the previous video, which was the elastic behavior in terms of interatomic forces. So I will not go into that, and that led us to the potential energy versus separation distance graph, the force, interatomic force versus interatomic separation graph. Now if we try to understand this with the help of a physical model, how we can mimic or how we can understand this interatomic force between atoms with the help of a physical model. So we can visualize the atoms present in the structure for this rigid body as balls or mass points which are connected to a spring. The two ends of the spring are connected to two mass points, which are balls, basically spherical balls. So the two ends of the spring are connected to two mass balls, spherical balls. Now we know the basic behavior of a spring. Okay, so a spring has a certain undisturbed equilibrium position. Now when the spring is stretched or it is compressed, it always tries to return back to its original stable position, and the force which helps it doing that, it is called as the restoring force. Okay, the restoring force is always opposite to the externally applied force. Okay, so you know that. We have discussed it in waves and oscillations in the simple harmonic motion playlist. So you can watch the concepts related to simple harmonic motion in the waves and oscillation playlist. Okay, so the restoring force helps the spring to return back to its original equilibrium position, mean position, after it is either stretched or compressed. The same behavior is exhibited by the interatomic forces in case of atoms here. Suppose we visualize this as atoms connected to spring. The two ends of the spring are connected with atoms. So it is exactly the same as the interatomic forces between atoms. So here the interatomic forces are the same. Okay, the interatomic force is the same as the restoring force of the spring. So basically the interatomic force tries to restore the atoms back to their original position. The same thing is done by the restoring force of the spring. So let us try to understand how it works. So we have these atoms connected, we have the mass points connected to the two ends of the spring. Suppose we have an external force. It tries to pull the two atoms away from each other. Okay, originally they are in the equilibrium separation distance. So when they are stretched, okay, by the externally applied deforming force, the restoring force of the spring acts in the opposite direction. So this is same as the interatomic force of attraction. The restoring force restores the two atoms back to their original stable equilibrium position. So this is the deforming force, externally applied deforming force, and this is the restoring force of the spring. So if you see, I told you that the restoring force of spring always acts in the opposite direction to the externally applied force. This is also the restoring force of the spring, acting in the opposite direction to the externally applied deforming force. Okay, the deforming force and the restoring force of the spring, they are always in the opposite direction, and the initial and final positions, they are the same. Okay, so this is when the spring is stretched, that is the two atoms, they move away from each other, that is the interatomic separation is greater than the equilibrium separation. Similarly, when the externally applied deforming force tries to compress the spring, that is move the two atoms closer to each other. So in this case the interatomic separation is lesser than the equilibrium separation. So here the restoring force acts in the opposite direction, as if it mimics the interatomic force of repulsion. So it acts again in the opposite direction to the externally applied force and tries to restore the spring back to its original equilibrium position, mean position. Okay, so this is the deforming force again, this is the restoring force of the spring. Again, this acts in this direction, this acts in the opposite direction. Restoring force is always opposite to the deformation force, and it depends on the distance away from the mean position, the displacement away from the mean position, and this is the spring constant. The same thing can be applied to the interatomic force as well. So basically what we are trying to do is to explain to you how the interatomic force can be explained in terms of a spring ball 3D model. So here these balls, they represent the atoms in a solid, elastic solid. These are all atoms, these white balls. And the springs, they represent the interatomic forces. Okay, these are all interatomic forces. All these springs, they represent interatomic forces between the atoms. Okay, so the balls represent the atoms, the springs represent the interatomic forces. So when the two balls, they move closer to each other, okay, the two balls, when they move closer to each other, the interatomic force acts in the opposite direction, which is basically the repulsive forces. and when the two balls they move away from each other, the interatomic force acts in the opposite direction, that is interatomic attractive force, okay, which is the restoring force of the spring. So the restoring force of the spring is the interatomic force. So let me again clarify here. The balls, the white balls, they represent the atoms, okay. The springs, basically the restoring force of the spring, that represents the interatomic force of attraction or repulsion. Okay, so this is just a physical model to mimic the interatomic model, to mimic the behavior of the atomic model for elastic solids. This is only applied to the elastic solids, okay, the elastic behavior, elasticity, because elastic solids, they return back, they regain back their original shape and size after undergoing deformation by an external force. So the deformation is temporary. So that interatomic force which restores the atom back to their original position, okay, that behavior is exactly the same as the restoring force of the spring, which tries to restore the spring back to its original mean position. Okay, so the mean position, again I am adding here, the mean position of the spring, the mean position of spring, that is undisturbed one, is the same as the equilibrium separation of atoms. Okay, so as the spring always tries to return back to its mean position, the atoms always try to return back to their equilibrium separation in elastic solids. This is only applicable for elastic solids. Okay, always remember this. Okay, so this is the explanation of the interatomic forces in elastic solids in terms of the spring ball 3D model. Okay.